We walk past them every day. We marvel at their height, their grandeur, their intricate details. But have you ever truly paused to consider how these massive buildings is broke? I mean, from ancient cathedrals that pierce the sky to the shimmering modern skyscrapers that define our cityscapes, how they actually get built. I mean, just imagine, how do you get materials and, crucially, people up to those dizzying heights to lay stone, apply a delicate stucco finish, or install incredibly complex structural elements? It's a fundamental challenge, really, that humanity has wrestled with for millennia. And it requires an unsung hero, a temporary, often overlooked, but absolutely essential backbone.
Right.
Today, we're pulling back the curtain on that hero, scaffolding. We're diving deep into the fascinating world of the temporary structures that make all that permanent architecture possible.
And what's truly captivating here, I think, is that the sheer problem of working at height is as old as human ambition itself. From the moment we first wanted to build something taller than we could reach, well, the challenge presented itself. It's a foundational issue that has consistently driven incredible ingenuity throughout history, leading to an entire category of what we can genuinely call temporary architecture.
Temporary architecture, I like that.
Exactly. These are structures that, despite their fleeting nature, are absolutely critical to the creation and maintenance of virtually every permanent building we admire. They are the unseen enablers, the silent partners in construction.
And our mission in this deep dive, then, is to give you a true shortcut to understanding this incredible journey. We'll explore the evolution, the meticulous engineering, and the absolutely essential role of scaffolding. We're going to celebrate these often invisible platforms that literally elevate the craftspeople who bring our buildings to life, allowing them to perform their artistry safely and precisely at any height. We'll trace its journey from some surprisingly simple yet ingenious solutions unearthed in antiquity, all the way to the complex, safety-driven, modular systems that are fundamental to modern construction.
You can expect us to unearth archaeological clues still visible in ancient Roman structures, to marvel at the monumental efforts of medieval cathedral builders, and to track how the very materials of scaffolding have transformed over time, from humble wood to sophisticated steel and aluminum.
Right.
We'll delve into the rigorous safety standards and cutting-edge engineering principles that stand behind modern scaffolding, ensuring that those who build our world can do so safely and efficiently. So let's begin our ascent, I suppose, exploring the platforms that build our world.
Okay, so if our mission is to understand how we conquer height, where better to begin than with humanity's earliest monumental structures and the silent clues they still hold about their construction? When we conjure images of ancient wonders like the Roman Colosseum,
Oh, yeah.
our minds are often captured by its sheer grandeur, its enduring strength, and the incredible scale of its design. But if you look incredibly closely at its exterior walls, you might just spot some enduring, almost humble clues about how these monumental structures were actually erected. What do these ancient buildings whisper to us about their temporary supports?
Indeed, they do whisper. The systematic pattern of holes you can still observe in the exterior walls of structures like the Roman Colosseum, often mistaken by the casual observer as just, later damage or natural wear and tear, actually reveals a sophisticated and highly organized early form of scaffolding.
Really? So those holes had a purpose.
Oh, absolutely. These weren't random imperfections. They were precisely placed anchor points, meticulously engineered, it seems, to receive massive wooden beams. Imagine these sturdy timbers, maybe a foot or more in diameter, inserted horizontally into these openings,
Okay.
creating a robust, temporary framework that encircled the entire structure. As the construction progressed, layer by laborious layer, new levels of this wooden scaffolding would have been built up, resting on these projecting beams.
Wow.
And this allowed legions of workers to access the upper levels to lay stone, hoist materials, and perform their intricate masonry work. This systematic approach, repeated hundreds or thousands of times across the Colosseum's vast circumference, it demonstrates an understanding of modular construction and temporary access that, while, let's say, rudimentary by today's standards, was profoundly advanced for its time.
That's incredible.
It's a powerful insight into the engineering mindset of the Romans, proving that even thousands of years ago, builders recognized the fundamental, non-negotiable need for external, temporary support to construct and finish monumental masonry work. Their ambition for permanent structures was directly enabled by their ingenuity in temporary ones.
That's a powerful visual. It makes you realize that building these wonders wasn't just about stacking stones, was it? These ancient buildings, while massive and awe-inspiring, also had incredibly detailed, often delicate finishes that required precise artistry and a steady hand.
Exactly.
I just can't imagine how they managed those intricate finishes high up on the walls without something incredibly stable.
Absolutely. The structural integrity was one challenge, but the aesthetic perfection was another entirely, and it was equally reliant on scaffolding. Take, for instance, the architectural treatises of Vitruvius, the Roman architect and engineer.
Right, Vitruvius.
He didn't just discuss foundations and columns, he meticulously detailed the construction of classical temples, specifying not only the precise heights and thicknesses of columns, but also the critical need for a smooth polish of the stucco on walls.
Smooth polish, high up.
Exactly. And this wasn't a quick slapdash job. Vitruvius himself warns that stucco could blister or break up if not properly applied, highlighting the delicate chemistry involved. The process of slaking lime for stucco, which is essentially hydrating quicklime to create a workable paste. While it required careful preparation, precise temperature control, and a skilled hand to achieve the right consistency.
Wow, okay.
Now imagine trying to manage that delicate chemistry, applying this sensitive material to a vast high wall or meticulously carving details into a fluted column, all while balanced on a wobbly, insecure platform.
Yeah, no thanks.
It's simply impossible to achieve that level of precise aesthetic work without stable, reliable platforms. The scaffolding wasn't just supporting the worker, it was, in a way, supporting the very chemical integrity and holistic intent of the material itself, ensuring a perfect, lasting finish that still amazes us today.
Hmm.
This reinforces the idea that highly competent labor, supported by these stable, temporary platforms, was absolutely essential for achieving those high-quality finishes that define classical architecture.
That attention to detail, even in the chemistry of materials, is truly remarkable. It makes you appreciate every facet of those ancient structures. Okay, so from these ancient anchor points in Roman walls, humanity's ambition only grew, quite literally, reaching for the heavens.
Right.
And with that ambition came new challenges as we fast forward to the Middle Ages and the soaring cathedrals. These structures weren't just incredibly tall, they were intricate works of art and engineering, often built over generations, involving countless specialized craftspeople. It must have been a completely different scale of temporary structure needed then.
A vastly different scale indeed. The medieval cathedral builders, as recounted in texts like The Cathedral Builders, embarked on constructing edifices so vast that the crowds could enter the sanctuary, demanding immense height, unprecedented spans, and incredibly intricate internal and external work that stretched skyward.
Just mind-boggling scale.
Totally. And this period saw the rise of a highly skilled and often itinerant population of stonecutters, masons, glaziers, and sculptors. These craftspeople were true artisans, moving between iconic sites across Europe, from the majestic Mont Saint-Michel to the towering cathedrals of Le Mans, Notre Dame de Paris, Reims, and Strasbourg.
Wow.
They carried their specialized knowledge and techniques with them, constantly on the move, bringing their skills to different projects over decades, sometimes centuries. Their work, however, was fundamentally reliant on stable, temporary access structures that grew synchronously with the building itself,
Right.
providing not just platforms, but the entire infrastructure for this monumental, multi-generational endeavor. Imagine an entire temporary wooden city rising alongside the stone.
A temporary city. And when you think about the sheer size of the stones, the vaults, the stained glass that needed to be lifted to such incredible heights for these cathedrals, that must have required some truly serious engineering for the time. Not just for the scaffolding itself, but for the lifting mechanisms too.
It certainly did. This wasn't merely about getting people up. It was about getting enormous, heavy materials up safely and efficiently. One of the key innovations that allowed such feats, specifically mentioned in relation to the construction of Beauvais Cathedral in France, was the tread wheel.
A tread wheel, like a giant hamster wheel for humans.
Pretty much, yeah. This wasn't just a simple rope and pulley. It was essentially a giant human-powered crane, sometimes large enough for 2 or more men to walk inside it. These immense devices were absolutely vital for raising enormous, multi-ton stones, timber beams, and other heavy materials to the immense heights required for these soaring Gothic structures.
That's incredible.
Now, such a device couldn't just operate from the ground with ropes trailing for hundreds of feet. It needed to be precisely integrated into and supported by the temporary structures that ascended with the building.
Ah,
The scaffolding, therefore, wasn't just a workspace. It was a dynamic, load-bearing framework that housed these lifting mechanisms, providing the essential infrastructure for all those heavy elements to reach their designated place in the heavens. It represents a complex interplay between temporary access and temporary lifting technology.
it's astonishing to consider the physical effort and coordination required for that. And tragically, Beauvais Cathedral also stands as a very stark reminder, doesn't it, of the inherent dangers involved in building so incredibly high, pushing the limits of both material and temporary structure.
Absolutely. It's a sobering historical lesson. Beauvais Cathedral's vault, which was designed to be the tallest in the world, collapsed in 1284. Yeah, and it's explicitly mentioned in historical accounts. This catastrophic event powerfully underscores the critical importance of stability and proper engineering, not just for the permanent structure itself, but equally, if not more so, for the temporary supports that enabled its construction.
So the scaffolding could have been part of the issue.
Well, the collapse wasn't just a failure of the permanent design. It highlighted the complex stresses and strains on the entire system, including the scaffolding that held everything in place during construction. The safety and integrity of scaffolding were, even then, literally matters of life and death for the craftspeople whose lives depended on these temporary structures.
Mm-hmm.
The lessons learned from such failures, often tragically, directly informed future building practices, leading to more robust designs and a greater understanding of the forces at play. It's a chilling reminder that human ambition often outpaces initial understanding, and that even the grandest visions are always tethered to the very real limits of physics and engineering.
It's a powerful reminder of the human cost when things go wrong and the constant learning curve of construction. So, from those ancient wooden beams anchored into Roman walls to the medieval tread wheels lifting stone for cathedrals, the basic problem of working at height has remained constant throughout history. But the materials available to builders and their understanding of how to use them have certainly evolved dramatically over time. I imagine for many centuries, wood was, well, the only real option, right?
For many, many centuries, wood was indeed the primary, if not sole, material for scaffolding. It was abundant, relatively easy to work with, and strong in certain applications. However, as sources like Understanding Wood remind us, wood, while incredibly versatile, has inherent limitations that profoundly shaped construction.
Like what specifically?
Well, its strength can vary significantly depending on the species, how it's cut, and especially across different grain directions. It's also highly susceptible to environmental changes. Moisture can cause swelling or shrinkage, leading to warping or splitting, and it's vulnerable to, rot, insect infestation, and fire.
Right. All the stuff wood does.
Exactly. Ancient and medieval builders had to become master craftsmen in maximizing its properties through clever joinery, interlocking joints, intricate lashing, and careful design, while always working within those very real natural constraints. Imagine the constant battle against rot, against warping under a sudden rainstorm, or the sheer difficulty of sourcing perfectly straight, massive timbers for hundreds of feet of scaffolding.
Yeah, that sounds like a nightmare.
These weren't minor inconveniences. They were fundamental design constraints that limited both the height and the lifespan of these temporary structures, dictating building forms and even how high we could truly aspire to reach.
That truly frames human ambition as literally negotiating with the tensile strength of a tree for millennia. It begs the question, was there a specific catalyst or a gradual realization that wood just wasn't going to cut it for our grander visions? When did we start to see that fundamental shift from predominantly wooden structures to something more engineered, more standardized, and more robust?
That's a great observation, and the shift was indeed both gradual and catalyzed by new architectural ambition. The very same source, Understanding Wood, offers a crucial clue, noting that metal, whose strength is clearly greater than that of wood, can be used to limit swelling or shrinkage of the wood.
Ah, interesting. A little foreshadowing there.
Exactly. This statement, almost prophetic, foreshadowed the eventual shift away from wood as the sole scaffolding material. As architecture became more complex and began reaching truly unprecedented heights with the advent of modern construction techniques, think of the early skyscrapers that Frank Lloyd Wright watched grow in Chicago as described in Space, Time, and Architecture.
Right, the birth of the skyscraper.
The inherent limitations of wood became increasingly apparent. The need for more robust, more predictable, more reusable, and precisely engineered temporary structures became paramount. Wood was simply too variable, too heavy for its strength, and too labor-intensive to erect and dismantle for the speed and scale of modern building.
It couldn't keep up.
It couldn't keep up. This critical demand led directly to the widespread adoption of steel and later aluminum in modular scaffolding systems. This was a true paradigm shift, not just a stronger material, but one that enabled standardization, reusability, and a whole new level of structural predictability for temporary works.
So these new engineered materials, steel and aluminum, didn't just offer greater strength and predictability, did they? They must have opened up entirely new possibilities for what permanent structures could achieve, because the temporary ones could be so much more adaptable and reliable.
Exactly. This is where the profound impact lies. These new engineered materials allow for incredibly intricate construction details and support the precise work required in modern building, enabling architectural forms that would have been, well, frankly impossible with wood-based scaffolding.
Like what kind of things?
For instance, consider the construction of a reinforced concrete masonry wall, particularly one built within the frame of a building, as detailed in Fundamentals of Building Construction. These walls, often serving as firewalls, need to extend continuously from the foundation right up to the parapet,
Okay.
requiring consistent, stable platforms at every single stage of their construction, with workers maneuvering rebar and mortar at height. The precision needed to ensure vertical alignment and structural integrity is immense, and it relies entirely on the unwavering stability of the scaffolding.
Right, you need that solid base.
Absolutely. Similarly, the installation of cellular steel decking for multi-story floors, think of it as prefabricated metal floor sections with hollow channels designed into them, much like a sophisticated honeycomb.
Oh, okay, I think I know what you mean for wiring and things.
Exactly. These channels are incredibly efficient for running electrical and communication wiring within the floor itself, making for a cleaner, more adaptable building. Installing these heavy, precise sections, especially across wide open spans high above the ground, absolutely relies on the unwavering stability of scaffolding to ensure everything aligns perfectly and safely and to protect the workers installing them.
So much more complex than just holding people up.
Oh, yeah. What this really means is that modern scaffolding isn't just a stronger version of old timber. It's a dynamic, adaptable, and highly intelligent temporary skin that allows the permanent structure to be built with an entirely new level of control, speed, and precision, integrating with the construction process in ways ancient builders could only dream of.
So we've come a long, long way from those simple anchor holes in Roman walls to the sophisticated steel and aluminum systems of today. It's clear that modern scaffolding isn't just about getting workers up high. It's about doing it efficiently, safely, and with incredible precision, enabling the complex, often gravity-defying architecture we see all around us. It's almost its own kind of temporary city that springs up around a building, like you said.
That's a wonderful analogy, a temporary city indeed. Modern scaffolding is truly a temporary architecture in its own right, purpose-built with immense engineering foresight to enable the permanent structures we inhabit. It's a foundational tool across all phases of construction, from the initial groundbreaking right through to the final touches, providing the necessary access for almost every single task, no matter how large or small. Its versatility is, it's astounding.
And its versatility must truly be astounding given the diverse nature of modern construction, right? From the huge structural elements down to the most delicate finishing work.
It absolutely is. We see scaffolding used for fundamental structural work, like building those firewalls we mentioned earlier, which are required to extend continuously from the foundation right up to a parapet above the roof of a building, as Building Construction Illustrated meticulously explains. This demands a continuous, safe, and stable work platform for multiple crews, but it's equally crucial for the most intricate finishing work that demands absolute precision.
Like,
Imagine the detail involved in finishing a joint between panels of gypsum board to achieve a perfectly seamless wall, a surface so smooth it disappears under paint.
right, you got to get that perfect finish.
Or stapling a metal corner bead to an external corner to create that perfect, crisp architectural edge. These tasks, often overlooked by the casual observer, demand highly stable, adjustable platforms that allow craftspeople to work with precision, care, and the necessary leverage. They simply cannot be rushed or done awkwardly from a precarious perch.
It sounds like it's also fundamental to everyday residential construction, too, not just monumental skyscrapers.
Yeah.
I picture window washers using suspended platforms, but the staging you mentioned sounds like it's much more widespread.
Absolutely. It permeates every level of construction. The book house, which delves into the craft of home building, even gives us a glimpse into this everyday use, describing carpenters who sit high up on the parapet of staging among treetops, diligently working on details like crown molding to the eaves.
Wow, up in the treetops.
Yeah, this staging is essentially residential scaffolding, providing that elevated, stable workspace for skilled craftspeople to perform their art cutting and fitting delicate, decorative moldings with handsaws and planes, often with an almost surgical precision. And it extends to other details, too, even aesthetic elements like installing metal roofing sheets with their ingenious systems of joining and fastening, which create distinct visual patterns and must be perfectly watertight, require craftspeople to work meticulously at height, relying heavily on the stability and accessibility provided by scaffolding to ensure both a durable, beautiful finish and, crucially, weatherproofing.
Right.
Without that stable platform, these tasks would be far slower, more dangerous, and the quality would suffer immensely.
It's easy, as you said, to see scaffolding as just a collection of poles and planks, a temporary eyesore on a construction site.
Yeah.
But you're really emphasizing that there must be a serious amount of engineering and design intelligence behind its creation, right? It can't just be slapped together.
Yeah.
I'm genuinely curious about the hidden complexity now.
You've hit on a critical point. It's absolutely not slapped together. The philosophy of engineering, as eloquently laid out in The Existential Pleasures of Engineering, applies perfectly here. The main goal has always been to understand the stuff of the universe, to consider problems based on human needs, to propose solutions, to test and select the best solution, and to follow through to a finished product. Scaffolding is precisely a design product. Every component, every joint, every connection point is meticulously engineered, and its design directly impacts not just efficiency, but crucially, safety. It's a testament to human ingenuity in solving a persistent, high-stakes problem.
So it's not just about individual components. It's a whole system that needs to be thought through, much like the permanent building it supports, but with the added complexity of being temporary and often dynamic.
Precisely. The principles of systems thinking are paramount here. Thinking in systems highlights the importance of proper design to understand a structure's limitations and bottlenecks, using it with maximum efficiency and refraining from fluctuations or expansions that strain its capacity.
Right.
This holistic, systemic approach is critical for temporary structures like scaffolding. They must be strong enough to bear incredibly heavy loads, not just workers, but tools, materials, and sometimes even heavy machinery, and yet be flexible enough to adapt to varied tasks, building geometries, and dynamic conditions like wind and changing loads. Modern engineering, as towards a new architecture, points out in its discussion of engineers in modern workshops and yards who design our bridges, ships, and airplanes, extends directly to the sophisticated design of these temporary works. This ensures that modern scaffolding meets rigorous performance criteria, including load-bearing capacity, stability against overturning, and resistance to environmental forces, making it a reliable, high-tech partner in every construction project.
Wow.
Engineers calculate everything from the number of ties to the building to the maximum weight per platform, ensuring safety and functionality.
When you're working so many stories up in the air, with heavy materials and complex tasks, often in unpredictable weather, safety must be the #1 paramount concern. The risks are simply too high to ignore any shortcuts.
Without a doubt, safety is not merely a concern. It's the absolute non-negotiable priority on any job site involving scaffolding. Construction management standards place immense emphasis on robust safety protocols, which are critically important for all scaffolding operations, from its initial erection to its final dismantling.
Okay.
This includes having a dedicated safety representative on site, someone whose job it is to oversee and enforce these protocols, and conducting daily inspections of all construction activities, particularly those involving elevated work, for compliance with established safety criteria. It's a continuous, proactive effort, not something you check off once and forget about.
And what happens when an unsafe condition is identified during one of these inspections, or if a hazard arises unexpectedly? How are those addressed in real time?
Any deficiencies or imminent hazards, anything that poses an immediate threat to life or limb must be addressed immediately. This involves issuing written notification to the contractor, detailing the issue, and ensuring it is followed up diligently with corrective measures until the situation is fully resolved.
Okay, so there's a process.
Oh, yeah. In severe cases where the risk is too high or the contractor is unresponsive, stop work orders can be issued by the construction manager. This halts all activity in the affected area until unsafe conditions are fully rectified. This isn't just a suggestion, it's a non-negotiable step to protect lives.
Right.
Furthermore, a crucial proactive measure is the job hazard analysis, or JHA. This is required prior to the performance of all critical, high-hazard, or non-routine activities.
And scaffolding definitely counts as high hazard.
Absolutely. Erecting and using scaffolding clearly falls into this category. A JHA systematically identifies potential hazards of each task, assesses the risks, and outlines the specific steps and controls needed to perform the work as safely as possible, minimizing risks before they even materialize.
That's a robust theoretical framework, with both proactive and reactive measures. But as we know, the unpredictable reality of a construction site can throw curveballs. Can you walk us through a real-world example of how these protocols spring into action when something does go wrong and what lessons are learned from it?
Absolutely. The Practitioner's Guide to Essential Lean Research 1 gives a powerful, real-world example. A construction worker was injured when struck by a wrench dropped from a higher elevation.
Ouch. Yeah, that happens.
Exactly.
So,
This immediate, tangible incident, which could have been fatal, led to specific and immediate procedural changes, such as stopping work in areas directly below elevated tasks until stringent safety steps are taken, like deploying netting or using tool tethers.
makes sense.
This highlights the very real and immediate risks involved and how incidents, unfortunately, drive the evolution of safety protocols. But it doesn't stop there. Beyond immediate correction, the detect, correct, analyze, prevent, or DSAP cycle is applied to all accidents near misses. This means not just fixing the immediate problem, like retrieving the wrench and ensuring no one else is below, detect and correct, but truly analyzing why it happened. This might involve techniques like the 5 whys, where you keep asking why, to drill down to the root cause. Why was the wrench dropped? Why wasn't it tethered? Why was someone working below?
Getting to the bottom of it.
Precisely. Only by understanding the deeper causes can you develop robust countermeasures such as mandatory tool tethering programs or improved communication protocols to prevent similar incidents from ever happening again. This continuous improvement cycle is absolutely essential for making construction sites safer over time, turning every incident into a learning opportunity that protects future workers.
That real-world example truly brings home the constant vigilance required and the systematic approach to learning from mistakes. Ultimately, as highly engineered and critical as it is, scaffolding is still a tool, isn't it? A means to an end. It's about empowering the people doing the actual work. It's about enabling the craftspeople who are bringing these buildings to life.
Precisely. That's the core of it. Scaffolding is, at its heart, about providing a safe and stable platform for the craftspeople who bring our buildings to life. Think again of the meticulous work of carpenters using handsaws and block planes for shaving saw cuts to near perfection on staging, as beautifully described in the book house.
Yeah, that image stuck with me.
Scaffolding literally elevates their skill, giving them the secure foundation, the comfortable posture, and the unimpeded access they need to perform their precise work at any height, whether that's installing a delicate crown molding or aligning a heavy stone. Shop Class as Soulcraft speaks eloquently to the inherent value of skilled manual work and the objective standards that provide agency and dignity to craftspeople. Scaffolding is the unsung enabler of this agency in building large structures, allowing skilled hands to perform their art safely, efficiently, and to the highest quality, no matter how high off the ground they might be. It transforms a dangerous, awkward task into a precise, manageable craft.
Beyond the traditional supported scaffolding, we often see hugging the side of a building. The principles of temporary structures for reaching difficult heights or positions extend to other impressive engineering feats, don't they? It's about creatively solving unique access problems for any large structure.
That's a great distinction, and it perfectly illustrates the broader genius behind temporary engineering solutions. Consider Isambard Kingdom Brunel's approach to building and launching his massive ships, as detailed in his biography.
Brunel always pops up with something clever.
Right. He faced an immense challenge during the construction of ships like the SS Great Britain. The ship's forefoot, its bow, could be 40 feet in the air during construction.
40 feet.
Yeah. While this wasn't a building in the conventional sense, it presented a very similar problem to architectural scaffolding. How to access and work on a large, complex structure at a significant, awkward height, allowing for intricate work on its hull and keel.
Okay, so how did he solve that one?
And Brunel, being the visionary engineer he was, came up with an equally visionary solution, didn't he? It wasn't about building up necessarily, but about ingenious horizontal movement.
Huh?
Indeed. Brunel's solution was a mechanical patent slip fitted with wheels or rollers. This was a truly revolutionary design that allowed the massive ship, once completed, to be built parallel to the river and then launched sideways.
Sideways launch.
A remarkable feat of engineering in itself for its time. What's particularly ingenious and relevant to our discussion, however, is that this slip could also be moved and re-erected at the port for future maintenance and examination.
So it was reusable, like modular scaffolding.
Exactly. It wasn't just a one-time launch mechanism. It was a reusable, temporary, elevated work platform for the entire lifespan of the ship. While not traditional building scaffolding composed of poles and planks, it perfectly exemplifies the ingenuity applied to creating specialized temporary elevated work platforms for monumental projects, pushing the boundaries of what temporary structures could achieve.
Yep.
It's the same core problem-solving mindset, how to safely provide access to a large, complex, and high-up structure, just applied to a different kind of monumental structure. It shows how the principles of temporary architecture extend far beyond just buildings.
What an incredible journey we've taken today. Seriously, from simple, precisely drilled holes in ancient Roman walls, through the human-powered tread wheels of medieval cathedrals, to the complex engineered systems of today, and even to the ingenious solutions for launching giant ships. It's all in service of human ambition to build, to create, and to reach new heights, literally and figuratively.
It really is. This deep dive has shown us that scaffolding is far more than just a temporary structure or a collection of poles and planks.
Wow.
It's a profound testament to human ingenuity, a critical enabler of architectural possibility, and a silent yet foundational partner in every grand structure we marvel at. It's a constant evolving reminder of the immense craft, labor, and dedication that goes into shaping our built world, elevating not just materials, but the very hands that shape them.
We've traced how scaffolding has evolved through the ages, adapting materials and engineering to meet ever-growing challenges. From humble wood to sophisticated steel and aluminum, it has always prioritized the safety and capability of the craftspeople working at height, ensuring their skills can be fully utilized. It truly is the temporary architecture that is essential for creating permanent architecture.
So, the next time you look at a towering building, a historic monument, or even just a house undergoing renovation, take a moment to appreciate the invisible, temporary framework that made it all possible. Think about the platforms, the people who worked on them, and the incredible precision required, all supported by this unsung hero of construction.
And maybe let that thought extend even further. What hidden temporary structures, both physical and conceptual, are enabling the permanent buildings of our lives today? From the scaffolding of a nascent idea in your mind to the support systems for our daily routines, or even the temporary frameworks we build to achieve our personal goals. Where do you rely on temporary platforms to reach your aspirations?